Greetings, Saintsmen. We're going to start lesson 9.1 on the Pythagorean Theorem. We're going to do a proof of the Pythagorean Theorem, which we haven't done yet. It's one of these things that you guys have had told to you and you've learned by rote. Goodness, I'm still having issues with this pen. But you may have learned in middle school this notion that a squared plus b squared is equal to c squared. Why? What does this even mean, right? So there's a few things. One of the ways we're going to go about proving this is actually showing the one of the great algebraic mistakes that I see, and that's one of my algebraic pet peeves. But the real summary here is this: what this actually is. And a squared, b squared, and c squared, it's referring to within a right triangle that we have a number of parts. Now we're going to have a right angle, right? The side that's opposite is what is called the hypotenuse. Let me rewrite that for you guys, the pen is just illegible. Hypotenuse, okay? That, of all these three letters, is going to be the letter C. The other two are the legs. The two parts of this triangle, and any of those legs are interchangeably A or B. But when you take the sum of the two legs squared, is going to be equal to the hypotenuse squared. Now, what this does mean is the following. It means that we can disregard some things here. One of my big algebraic pet peeves is seeing a squared plus b squared is equal to a plus b squared, which is just nonsense. It's just not the case. All right. Just think about this. 3 squared plus 4 squared, right, is not 3 plus 4 squared. 3 plus 4, right, if you were to put that into these parentheses, is going to be 7. 7 squared is 49. 3 squared is 9. 4 squared is 16, right? That's not going to be equal to 49 when we take the sum of those two things and square them. So, going to do a little combo graphical / algebraic proof with you guys right now as we take a look at this. So, we're going to take two squares side by side. All right. First and foremost, we have figure 1. All right. So I'm going to subdivide both of these figures. Now, they're identical squares. So we should know that their two areas are going to be the same, but we're going to subdivide them in the following way. That we have this length coming across, that's going to be A and B. Now, same length A, I'm going to take off of this side on the left of the square, or this square figure. So this is going to be subdivided again into A and B. All right, now, if I were to take an auxiliary line across the figure, we're going to solve for areas of each of these, right? So let's take this first area right here, right? And the top right. That's going to be side times side, which is b times b, or in other words, the area of this portion is going to be b squared. Of this rectangle right here, right, we're going to take an area, side times side, which is a times b, or ab. Bottom left corner, we have the small square, a times a, which is a squared. And then, of course, the last one of these is a times b, the last one of these rectangles. Now, again, let's subdivide this second figure, which is, again, identical to figure 1 in size. But we're going to, again, subdivide our sides A and B. But we're going to do it A and B for every single side all the way across. It's still the same figure, right? A and B still have the same lengths, but I'm going to go ahead and create these auxiliary lines connecting each of these intersections where A and B subdivide each side. Now, the side length for each of these, right, here is B. Now, we're going to find the area of this triangle, one of these triangles right here, right? Which is going to be the same for each of these triangles. A times, the area of that triangle is going to be 1/2 of the base times the height, or A times B, right? And it's the same for all of these 4 triangles. Same. Hope you guys are still following me here. Now, what we don't have is this third side right here. But again, if this is a square, that's a right angle, so it's a right triangle, meaning that we can just call this side C. It's identical for all of them, right? It's all side C, so the area of that square is going to be C squared. Now let's take and compare figures 1 and 2 in terms of their area. We know that those areas are the same. They have to be. They're identical figures. All right. So the area figure 1. A squared, right? We're going to take a composite area, sum of all these areas, plus B squared, plus those other 2 ABs, so 2AB, right? And then we have, for the way it's subdivided for figure 2, we have C squared, and then we have all those 4 triangles, 1/2 AB, 1/2 AB, 1/2 AB, and of course, 1/2 AB. Now, let's go ahead and simplify these, right? So, we have A squared plus B squared plus 2AB, right? We have C squared, and then we're going to take the sum of all these. 1/2 AB plus 1/2 AB plus 1/2 AB plus 1/2 AB is going to be equal to 2AB. If I'm solving for this, right, I'm going to subtract off 2AB, which, of course, if I take it off from each side, right, if I take it from the right, I have to take it off the left, which leaves me with the following. We should know that, algebraically, we've proven that A squared plus B squared, right, is equal to C squared. And this, gentlemen, is proof of the Pythagorean theorem. Let's go ahead and employ this in a couple of problems, okay? We're going to employ this first in an example that's going to be very similar to what you guys are going to do for your homework. And then I've got some other problems for you to take a look at as well, in terms of how we classify triangles by angle, and we can do that just using the Pythagorean theorem. All right, here's our right triangle. X, 3, 6, and we're going to solve for x. All right, so remember what this means. A squared plus B squared is equal to C squared, right? So, here are our legs, A and B, 3 and x. Because the hypotenuse is going to be opposite the right angle, so this right here, 6, is going to be my C squared. So, 3 squared plus x squared is equal to 6 squared. Typically, what some students are going to do is they're going to want to make this all equal to x squared, and that's not the case, right? We always have to make it equal to the hypotenuse squared. Doesn't matter if we have x squared or 3 squared first? Well, no. The commutative property means that we can switch the order of these two things, right? They can go in either order. So 3 squared, which is 9, plus x squared is equal to 6 squared, which is 36. Subtract 9 from both sides. X squared is equal to 36 minus 9, which is 27. And then how do we get the x by itself? Well, we have to undo the operation being done to x, which is squaring it. So we'll take a square root. X is now by itself. Then we can get the square root of 27, rad 27, which is going to be 3 times the square root of 3, right? 9 times 27 is, I'm sorry, 9 times 3 is 27. Square root of 9 is 3, comes out. Rad 3 is left inside. So that is our answer, 3 rad 3. This is a special right triangle that we are going to come back to in our next lesson. So don't forget about this guy. We're going to determine if the triangle is right obtuse or acute. Now, let me show you guys step 1, and here are our dimensions. 10, 11, 13. Excuse me. So, taking a look at this. We have to actually determine if this is a triangle in the first place, right? Remember we did this back, goodness, this is back in the first semester, and we had to make a determination. So I have to go and add up and see if the sum of two of the sides are going to be equal or greater than the third one, right? So we have to first check this, right? 10 plus 11 greater than 13. Checks out. 11 plus 13, of course, is going to be greater than 10. Both of those numbers are greater than 10. And 11 plus 13, 10 plus 13, which is greater than 11, right? So all of those are, all those three inequalities work out. So yes, it's a triangle. That's important, because if not, we're kind of just wasting our time. All right, so here's what we do. We see are the two legs. Now, the legs are going to have to be the two smallest of the sides, right? They have to be, because the hypotenuse has to be the largest side, because it's going to be opposite the greatest angle, which is 90, right? You can only have one right angle within a triangle, maximum. So 10 squared plus 11 squared equals 13 squared, which is not true, right? 10 squared is 100, 11 squared is 121, 13 squared is 169. So gentlemen, we know this is not a right triangle. Instead, we have the following, right? I just gave you those dimensions. 121. And what's its relationship? Well, it is greater than 169, right? Because 221 is greater than 169. Now, if two of the sides are greater than that third side when squared in this way, right? Of the two smaller sides, this is going to only have one of two options. It's going to be obtuse or acute. If the two are greater, believe it or not, this is going to be, right? If you were going to guess, it means it's going to have to be acute, and that is the answer. You have to think about this, and I'm going to mark this guy out here. I want you guys to think about the hinge theorem, right? So let's say I have these, we have a right triangle. Let's take a quick one, 3, 4, 5. Okay. If I increase this side, right, and I have a 5 right here, and I increase this guy to 4.5, this is no longer a right triangle, right? And if this has increased compared to what it was before, when there was the 4, then I'm going to have to decrease this hypotenuse, right, in order to make the sides connect. I don't know if that makes a lot of sense. It's easier for me to show you in person, but we can explore this a little bit with the, I've got some software that we'll take a look at in class together. So this will get you guys started, give you a background for this lesson. We're going to be doing a lot of a squared plus b squared is equal to c squared. The key is getting the correct parts of the triangle filled in for the appropriate variables of a, b, and c. So good luck, gentlemen, and I will see you in class.